So good morning once again, everybody. This time around, I am joined by some folks, including Mark Freilich from Analytical AI. Gentlemen, the stage is yours for 20 minutes. As I mentioned at the top of the event, there's no time or allotment for Q&A during these sessions. This is meant for you to have the mic for 20 minutes, and I'll see you back in about that amount of time. Gentlemen, take it away.
Good morning, everybody. I am Mark Freilich, the CEO of Analytical AI. With me this morning is Thomas Anthony, co-founder and chief information officer, as well as Frank Skidmore, co-founder, and our vice president of research and development, and William Monroe, our chief data scientist. We're an early stage company based in Birmingham, Alabama, and our initial product was artificial intelligence for stroke detection. We have since pivoted to security after the Kaggle competition for the TSA passenger screening challenge. We've done work with DHS, TSA, Sandia, and some of the OEMs, as well as we have deployed automated threat recognition algorithms and testing at TSA. The underlying AI for healthcare and for security is extremely similar, and so we are continuing to remain in the healthcare realm as well as the security realm.
Hey, I'm Thomas Anthony. I'm one of the co-founders and the chief information officer. I lead the AI development for Analytical AI. So our capabilities, there's just a quick brief of what our capabilities are for us. Whether it is a CT image that comes from a baggage scanner or a CT image that comes from a CT scanner at the hospital, it's the same. We're trying to find something and help either the physician or the TSO find that. So as part of that, we've built out an automated stroke detection and hemorrhage detection model with different types of the intracranial hemorrhages and their subtypes. We were actually among the winner's circle of the Radiological Society of North America's challenge when they put that out in 2020. We have automated threat recognition algorithms for on-person screening. That was as part of our other challenge win that Homeland Security had put out, and our solution was the one that was chosen for deployment. We have a newer on-person screening threat recognition technology AI that we have built, which is currently going in for deployment at Customs and Border Patrol. For most people who don't know that the TSA is moving away from the older two-dimensional X-rays to close to medical grade CT scanners at the airports to scan baggages, and we've built out algorithms for those as well, including threats that are prohibited items, explosives, as well as stream of commerce items. Now, in the world of AI, in order for you to develop the AI, you need to have a suite of tools in order to annotate that, and we've seen that especially in the healthcare realm. Back in the day when we started, we had our neurologist, one of whom is sitting next to me, Dr. Skidmore, and Raj Sangha, who's one of our other co-founders, who's a stroke specialist, who was basically sitting at a touch screen, marking out strokes on each slice, pixel by pixel of a DICOM slice of a stroke. And in order to speed that up, we've also built out an enhanced annotation suite that makes it a lot easier. Now, since we work in a high risk environment, we have to have a high reliability environment. We also have William Monroe, who's our senior data scientist. His entire dissertation was in explainability of AI. Most people, when they develop artificial intelligence softwares, it's kind of a black box, but that does not really work in the medical realm or in the security realm. We need to make sure that we are not probabilistic. As you guys know, most artificial intelligence is on a certain level probabilistic. So we have to have it be very deterministic. If the scan has gone through once and determined a value, it gives you the same answer if the scan goes through again. And so we can talk a little more about explainability of AI as well. And that's something that we are required to do. Now, as part of the Radiological Society of North America challenge, we built out a near real-time triage algorithm for ICH detection and classification. We did fairly well in that. And as you know, stroke versus hemorrhage is a very big issue. Frank can talk a little more about it, especially the time that you get TPA, the tissue plasminogen activator, from when you get a stroke to getting that clot buster is very important for outcomes. We could do that, and this is an example of what it is showing where the hemorrhage is in the image itself that was given to us. And we can, at this point in time, we started with the stroke model, but we've added an ICH model to that. So this can do it in near real time. And by near real time, I mean less than a minute after scan acquisition. So if the radiologist has something to look at, or even if it brings it up on the teleradiologist's read saying, hey, the algorithm says there could be a stroke or a hemorrhage, look in this area, or you need to look at this immediately, the outcomes might be better. Frank, you want to add some stuff?
Yeah, so I think that the history would be important. We were an academic medical laboratory, and we looked at things like Parkinson's, Alzheimer's, and my beginning was really using statistics and things like that to develop diagnoses. When AI came on, the laboratory, all of us started to shift towards big data, and essentially, we dealt with all kinds of images, from ultrasound to MRI scans, which are very high dimensional. So when Kaggle put out its algorithm, its detection algorithm, we had the ability to rapidly shift our stroke detection algorithms and basically train them on that. And within 6 weeks, we had a top solution that could give a solution for the TSA within 1.5 seconds?
About 2 seconds.
About 2 seconds, so. Yeah. So rapidity is very important to us. We want answers to come very quickly so that they're diagnostically useful. We've dealt with, we're talking about the stroke detection, but our Kaggle experience and our capabilities extend to things like emergency issues pertaining to the chest, for x-rays, and ultrasound. So we've done challenges in all of those domains and have experience, and that deep experience actually allowed us to pivot very effectively and provide rapid solutions for security. So we're still very engaged in the medical domain, what we're interested, though, is in practical solutions. We're not the type of company that takes a bunch of money and then wishes and prays that something will enter the market. We actually want to solve things now, and we want a stream of funding that goes along with it. And so when we pivoted, we basically took our medical technology, moved it to security, but it's fungible. It can go right back. This team has had a lot of experience together in this domain, and anyways, it's good to introduce this. And you know what? I think we're going to talk about some of the practical things that we've done with
just very quickly to at a 30,000-foot view. For warfighter health, what we can provide is a rapid assist to the physicians treating patients, whether it be incoming wounded or, in the Navy's case, on ship, where we can add items beyond stroke, beyond neuro, that would help with time to diagnosis very quickly, or time to what somebody should be looking at very quickly and very efficiently.
Yeah, so we were in this realm, we were dealing with those higher dimensional data with MRI, which was a minimum of 4-dimensional data before you add time as the fifth temporal, as the fifth dimension. When TSA came out with the challenge for detecting weapons on people, this is a machine you guys see at the airports. It was very similar data, and for us, it was like, if I can detect a stroke in the brain, I can detect a weapon on the person out there, which made it a lot easier for us to build it. And we actually have contracts for deployment of the solution. And that's what helped us pivot into the security space. Now, the next couple of slides that we're talking about show you some of the things that we've done in the security space, but that should not detract you from
Proof of concept.
what we have in the
It's the
medical
same stuff.
space.
Same stuff.
For us, an image is a 3-dimensional or 2 or 3-dimensional matrix of numbers, be it from a security scanner like this or a CT scanner. And that is what we bring to the table. For us, it is time to solution, how easily it can be deployed and how quickly we can train it through. And as part of that, we've built out, so this is the solution that is going in at Customs and Border Patrol right now. That is on-person screening solution. Again, very similar AI. These are algorithms which are not hypothetical that, okay, we have to go and test. So these are currently being tested and deployed in multiple locations. So this is no longer an academic project. It is an actual deployable solution. And this is something that we want to do. We have these rapid turnaround deploys. Once this company came to the TSA, they sent them to us and said, hey, talk to these folks. If they can build out algorithms for automated detection, we can start testing those. And we had something ready for testing in less than 12 weeks. So that's how quickly, once we get data, we can start deployment testing and integration. This is another example where it is the same CT scanner that you find in hospitals that is going into the airports, and we are detecting laptops, shoes, pretty much the same thing. So the concepts remain the same. You have tons of training data that you teach the algorithm to learn, identify, and classify, and that's exactly what we would be doing in the medical space as well, and that's what we do really well. We're talking about data at scale to teach it, and this is a very high trust situation. So unfortunately, due to SSI rules, I cannot show you anything that shows a weapon out here. But this is our stream of commerce algorithm that is actually detecting laptops and shoes, and we do the same thing. And it's the same companies that make the CT scanners for medical imaging that make it. The OEMs are pretty much the same on the back end. So the technology is close to identical, which can be implemented easily.
DICOS and DICOM.
Yeah, and this is an example of our 3-dimensional annotation tool that we built out. You can replace this bag with a brain CT and it would work just the same way, where we can rapidly annotate anything. So what that does is it gives us the ability to train our models really faster. Currently, this is a solution that we have developed, which is up to 20 times faster in annotating 3D images compared to what's available in the field for both medical and security images.
And we're by no means limited to CT. I know we talk about CT a lot, but any medical image is what we're capable of.
Yeah, chest X-rays, bone fractures, pneumothorax, the types of things that happen in emergent situations. We've actually dealt with that data, and we're comfortable with it.
We're also talking about MRI.
MRI as well.
Mammography.
Yeah.
Pretty much anything that's an image. For us, images are fungible. They are matrices of numbers for us. Now, all of this is good, but you need to have somewhere to put your algorithms on and have them run, take the data. So the TSA actually funded us to build an appliance like this. We have the initial patent in for an appliance like this, irrespective. So what would happen in a hospital kind of setting is multiple data generation sources. Those could be CT scanners, MRIs, X-rays, mammography machines would be sending data, and all the algorithms would actually reside on a system such as this. This is what we are building currently for the TSA. But the patent is written in such a way that it covers both security and medical, so that this platform can host all of the algorithms and send those outputs out as required back to either your PACS system, if you're talking about CTs, X-rays, MRIs, and also talk to your EMR systems in the medical realm. So you can move back and forth between them. So we don't have to add any more compute on the devices themselves. The devices at that point are just an imager. It's just a scanner. Since we work in these very high trust situations, it's not good enough that our algorithm performs well. For some reason, we have seen that if a human looks at a scan and reads it to about 50% accuracy, you still expect the algorithm to read it at 100% accuracy. And unfortunately, that is not the case. As you saw in one of our previous slides, it said the laptop, it was 97% accurate. The question is why? And for that, we have William's entire dissertation, which is published, is on this explainability of AI. Why did the algorithm do that? We don't like keeping black box models. We like opening up the black boxes and going back into the system, because for us, in those high reliability, high trust situations, what was it looking at and why it was looking at that to give you that level of accuracy, precision, and recall is what we look at. And that's something that's very important in both the security and the medical realm. And there are multiple studies that have shown that we hold those computers and algorithms to a much higher standard than we would hold a human looking at that.
This is practically useful for us in the security domain. So if somebody changes the baggage cart or something having to do with, and we train the model in one situation, and there's a slight change because the airport uses different bins. Sometimes that will throw the AI, and the question is, you have to ask the question why. What was it looking at? This kind of approach allows us to calibrate and problem solve and correct algorithms and train them to more specificity and also be more robust and reliable.
Yeah, and it would be the same in the medical domain as well. It would help us identify, was there a source of EMI, like you expect your CT scan or MRI rooms to be shielded well. What if there was some pipe work that went on in the room next door and they had to cut out some of that shielding? How did that affect the scanner as well? So that helps us explain why we do what we do in a way that it is more reliable. One thing that we would like to say is we are no longer a small stage early company. We have been in this domain for about 4 years at this point in time. We have a lot of wins under our belt. The TSA has funded us. We are under multiple Silicon Valley innovation programs. We have contracts directly with both the TSA and some OEMs as well who build these devices. And integration becomes a big part of it. So for us, integrating into an ecosystem, be it the security ecosystem or the hospital ecosystem, becomes fairly easy. I know we don't have, I see Krista pinging for a 2-minute warning. We don't have time for, we don't have Q&A as part of this, but you can feel free to reach out to any one of us. It's Mark at Analytical AI, Thomas at Analytical AI, Frank at analyticalai.com. I'm sure those links would be shared with you with the presentation.
And what we've shared with everybody this morning is our capabilities. And whether it be ultrasound again, MRI, X-ray, CT, any imaging, what we don't know is what the Navy's problems are that they would like to solve in this area and domain, what would be helpful, what is needed. But once we know that, we can respond and let the Navy know what is the art of the possible, what we can do, how it would work, and how we would integrate it. And we very much appreciate this opportunity and are very excited about the potential of working with the Navy. And we're hoping that what we have presented this morning is of interest. We think that whether it be triage, etc., we can be very helpful with medical imaging.
All right.
Thank you.
Thank you.
Gentlemen, thank you so much for sharing that with us this morning. It's a great way to end it, bringing attention back to, where do we start with the Navy? How do we get engaged? Who's out there to speak with? So hopefully through the venue we've created here and the engagement afterward, we'll get a chance to open some doors and get some interested folks in. So appreciate you all very much. Stay tuned. We're back in another 5 minutes with our next presenter. Thanks so much, everyone.
Thank
Thank you.